Thank you. Oh, I see. Yep. Thank you, Hannah. I saw your message. I didn't have my glasses on, so I missed it. Okay. So we were going over these things. So x squared is equal to py in the parabola. Parabola means equal areas. The ellipse means something's deficient. So we had x squared less than that rectangle. It's deficient. You need more stuff to fill it up. For the hyperbola, and somebody's hyperbolic, if they're over the top, they're more than they need to be. Well, in the hyperbola, we have x squared greater than py. So it's exceeding, or it means that it's exceeding. So those words that we use, they have these roots in ancient Greece. It's doubtful that they originated with Apollonius. I remember reading somewhere that they may go back pretty far. You saw people that were doing this, the cube doubling, saw the conics come up then, and they were back in the 300s and 400s. So those words could go back pretty far. Okay, I just wanted to make sure I go over that. So now when someone uses those words, you can do a bar bet and say, I bet I know what those words mean. I bet you don't. Okay, unless if they've had the history class. Okay, and I'll put up I made a couple of mistakes, and then I'll correct those in the last 3 bullet points and re-put it up there. Okay, so any questions about that? And that explains why we were so much focused on that square equaling the rectangle, how it related to it, because that's where the words came from. Okay, good. So I'm glad I got that done. Okay, so we saw how to generate a conic section last time, and we're going to do something similar today with a different curve. You'll be able from context to figure out what that curve is, I hope. And we're going to talk about, today we're going to talk about Archimedes, and I'm only going to scratch the surface of what he did. I'll talk a little bit about what else he did, and I'll post some things that he did. I was going to do that before class, but I got involved in something which I think is a better use of my time for this class, so I didn't post those things. And I'll show you what that thing is. But I'll post them. And I'll talk a little bit about what he did. But he's, if mathematicians who know mathematicians throughout history talk about their top 10 or even top 5, arguably top, he's on that list of very select mathematicians. And he did things like that we would consider calculus. He found areas of irregular objects using ideas which are similar to calculus. Those ideas didn't really come up again in a meaningful way for another almost 2,000 years. And everything he did, I mean, he was just he's very creative and very smart. And we'll see some very small examples of that today. So I did find a legal copy of the movie about Archimedes, and so I can post that, and I'll have something for that will come out this week. So relax for a day or two, and then I'll come up. And that'll be sort of the next kind of project we do. That'll be a short one. I'll probably give you some time off to watch the movie, and then we'll do another group project on non-Western mathematics, and I want to get into the Arab mathematicians a little bit before I give that, just to provide a little bit of context. I think I have everybody's homework. Make sure that you've submitted it if you didn't. There's COVID deadlines, which are not the same as regular deadlines. There's a lot of elasticity to them, but get them in. And I think I only got 3 of the presentations from the 4 groups. So I'm going to figure out who didn't send it in. But if your group didn't send in your presentation, do that, because I want to grade that at the same time that I grade the homework. Okay. And I hope to get all that stuff done over the weekend. Okay, so before I begin with Archimedes, you're going to want to download handout 11, and it'll be in the week 9 activities in the handout folder. So I'll let you do that. And while you do that, let me know if you have any questions about anything, and I'll give you a couple of minutes to get settled, you get the handout, and get it up there. Okay. But again, if you have any questions in the meantime, ask them. I'm going to get something to drink, and I'll be right back. And I'll stop the share. Yes, I had to show off my can, right? It's not beer. I wish it was. It's a seltzer. Okay. I just saw Paul's Paul's post. Okay, so when you look at 11, this was on the last handout. This is another curve, and you can figure out what it is probably by the title. That's not a bad thing, but look at that and try to make sense of that what curve is that. Try to make sense of how that curve is created. And I'm going to, in the meantime, get a couple of demos of that ready. So that's the first thing I want you to do. We're going to use this curve to square the circle and to trisect angles. Okay, so looking at that, anybody want to either you can chat it out or say something about why that's a spiral? Does it make sense to you that it would be? Are you getting a sense of how the construction works? Is it completely baffling or does it make some sense?
I think it makes sense.
Okay.
Because it's going to grow at a fixed rate away from the point, but rotating.
Yeah. Yes, it's rotating at the same time it's expanding. And it just draws a spiral. And I think your hand does that naturally. And I think of it if I had a compass and I had a servo motor in the compass that expanded at a fixed rate and I could turn to match that rate, I'd trace out a spiral. And so I want to show you a couple of ways to think about it. Of course, I have too many windows open. Which is the one? Okay, are you seeing a Desmos demo?
Yes.
Okay, if I turn that on, I have the polar coordinate, and I can go through that. That's one turn of the spiral, and so if I just play with the slider, and you can go to this site, it's all you can get it from the stuff in the week 9 folder. You can see it create just very slowly. And that's so right there. I've turned one circle 2 pi. I keep going. I'm going to go a whole nother circle. Okay. Or I can do it that way and you can kind of see it trace out. And so there's rotary direction and then there's the expansion direction. Okay. I'm going to show you a different version of it. Are you seeing a different version or the same one? Are you seeing a version that has like that's in blue?
It's different now, yeah.
Yeah,
It has
yeah.
the blue and the triangle.
And notice how one of the arms, as the red arm rotates, the longer arm keeps extending at a fixed rate. So I'm guessing that's something that the way that Archimedes thought about that. There was some pretty sophisticated mechanical devices back then. There's some calculating devices even. And there were some curves. These curves are called mechanical curves because they need a mechanism. It's not like a straight edge and compass. So if you're living in the straight edge and compass universe, these are some transcendence of that universe into mechanical curves. And one of the things that people did, mathematicians did, we know of a couple of other examples, they created curves to solve problems. And if you think about that, that's not a whole lot different what a mathematician might create a function to solve a problem. I think those of you who take physics are aware of examples of those kinds of special functions that people made because they were useful in a problem. Well, that's what you just saw was sort of the geometric version of that, the spiral. Yeah. Okay. So what I want to do is the handout goes through in detail about how to do it, how to square the circle. But if you follow it just by reading it, it's going to be so confusing. I have a Desmos demo of that, which I'll show you in a second that I made. But I want to go over one thing. So a spiral, a couple things actually. So a spiral, I gave the parametric form, but a spiral is usually, it's going to be a function in R that's equal to some constant times theta. And theta can be any real number. Usually theta is greater than 0, so it will rotate anti-clockwise. But you could have it, yeah, you could have it go the other way too. Okay. So this is the form of a spiral, and we're going to pick a special version of that. If this doesn't clear up, I'm going to restart my other camera. I know it's looking foggy to me. Is it foggy to you all?
Yeah, it's not
Yeah.
focused.
Okay, we'll see what yeah, it's been doing that lately. There it goes. It's easily distractible. It must have been focusing on something else. There you go. Okay, good. Okay, I'm going to show you a demo that I made, and I'll go back to. You have the URL on that sheet, but I'm going to go back to today's folder, and then I have the squaring the circle demo at Desmos. And this is what I was doing today instead of preparing handouts for you about Archimedes. I said, well, I don't know if you've all been into Desmos, but I've really got into it for my teaching and my pre-calculus class. And so it can do a lot of cool stuff. So what I wanted to do was I wanted to demonstrate what Archimedes did. And what he wanted to do is, well, I need to back up for a second. I'll come back to that. The other idea that I forgot to talk about, and it's on that sheet, is Archimedes Triangle. He proved through kind of a calculus inequality argument that if we have a right triangle, its height being the radius and the circumference, the base being the circumference of the circle, that the area of this triangle is equal to the area of the circle. And what I want you to do, just take a second and verify that, yes, the area of this triangle does indeed equal the area of the circle. And remember that the area of a triangle is base times width over 2, or base times height over 2. Everybody with me on that? You get the area? R times C, that's the area of the triangle, R times 2 pi R over 2 pi R squared. Now, the difficulty is in constructing this triangle. He proved that if such a triangle exists, this is true. But how do you construct the triangle? And that becomes the issue in Greek math. You have to somehow produce it. And how do you produce it? You can't with, they were unable to with ruler and compass. And it turns out, as I mentioned before, in the 1800s, it was proved impossible with ruler and compass. So the question becomes, how do I get this triangle? But before I do that, why does, if you could construct this triangle, why would that be tantamount to squaring the circle? And squaring the circle is, given a circle of radius r, construct a square of equal area. This constructs a triangle. If we have a method to construct a triangle, how does that give us a square? And without reading a lot of Euclid, you may not know this, but if you have a triangle, you can double it to get a, actually, I'm going to even go to something else. Euclid proved in book 2:14 that if you had any rectilinear figure, I'm drawing an irregular one, that you can, with a ruler and compass, find a square whose areas are equal. So in the world of ruler and compass, if you could construct this triangle, then you can square the circle. You can find a square whose area is equal to that of a given circle. So the question is, how do I construct the circle? And what Archimedes did is he used a spiral. And before I go on to that, that's what I'm going to do at Desmos. I'm going to show you the construction, and I'm going to have you go through some of the math. The proof of this is pretty amazing. It uses inequalities where you show that, in a way where you show that this triangle is indeed equal to this because it can't be any greater, nor can it be any less. And if you took Reals last fall, you no doubt saw some articles, some arguments where they use inequalities. That's precisely the way Archimedes' argument worked. It would fit in spirit to modern day analysis. That's called exhaustion. And if you read about the method of exhaustion, or if you met or Eudoxus and any of your other projects, he was the one that invented it in the 350s. The way that you show two things equal is you show they can't be greater than one another. One can't be greater than the other. One can't be less than the other. Then they have to be equal. Okay, that's what he did. Anyway, okay, so on to Desmos. I'll share the screen. And okay, so here's the demo. And again, you have it on the handout as well. And so I had to create like a bunch of yep, okay, good, yeah. So what I want to do is first, I want my spiral. I want one turn of the spiral. So I want r of 2 pi, which we know is equal to ar, little r, I'm sorry, a theta, to equal a given radius, which I'm calling capital R. Okay, and it turns out, and we'll go over that if I turn this once, so I make one turn of that radius, this point here is going to be R0. And again, plug in 2 theta into this and you'll see that. You'll see that little r is going to equal capital R. Okay. Now I built a slider, so this r can vary, but I have it set at r equal 1 just to make things. Okay, so he invented the spiral, and you saw his way of creating it. He took one turn of it, and so I'm gonna construct that triangle whose radius is whose base is the circumference and whose radius is the height. I'm gonna go through the method. You're gonna show that it works. So then he said, okay, we're at the spiral. You're seeing the spiral, right? At Desmos, I should have double checked.
Yes.
Yep,
Yep.
good. Okay. And then I'm going to create the tangent line to that point of tangency at one turn. So you're going to do that. And then that triangle that's formed by the axes and that tangent line, this triangle in here is equal to the area of the circle. And so I'm going to show, oops, sorry about that. I meant just to move this so the screen was a little bit better, but it's not cooperative. There we go. Okay. So I created the tangent line, and you see the three dots, you see the triangle, it's got a blue base and the green hypotenuse. The area of that triangle is equal to the area of a given circle. So circle of radius r, which you can construct, this triangle has the same area as that circle, and we're going to show why. And once you have this triangle, you can then create a square. Okay. So you're going to see that the base of that triangle, that's going to be equal to 2 pi. And then the sort of the height of the triangle here, that's going to be equal to r. And that's what I want you to show. So I'll just go through the construction again real quickly. That's one turn of the spiral. We draw the tangent line, take its intersection with the y-axis. We form the triangle between the two axes and that line, which I'm trying to indicate here. The area of that triangle is the area of the circle, and you're going to show why. It's because this is going to be equal to r. Along the x-axis part's r, and along the y-axis part, that's going to be equal to the circumference, 2 pi r. Okay, and what I did is I made this so, I'm going to zoom out, just so if we vary the radius, we still have that relationship. And so if we want the radius 2, that would be the triangle whose area is equal to the circle of radius 2, and so forth. Okay, so we're going to do one of these for the trisection too. Okay, before I go back, any questions about that? And again, you can download this in your computer. You can just click the link, and then if you want to do, have it open to play with. Okay. So I'm not seeing hearing any questions, so I'm going to go back. Okay. So what I'd like you to do is to go through the handout on the squaring of the circle, go through the bullet points, and your goal is to show, indeed, that triangle, the long side of that triangle along the y-axis, that's equal, that length is 2 pi r, and then the short side along the x-axis, that's radius r. And so so what the first thing you want to do is show that the formula I had was right, that we want a to be r over 2 pi, because we want r of 2 pi to equal r. Okay, that's going to be fairly easy. And then I'm guessing you don't know much polar coordinates, or some you do, some you might not. I'm guessing not everybody does. So this is the formula for how you find the slope of the tangent line at a given point. So r2 pi. And then once you find the y-intercept of that line, that'll give you the length of the triangle. So I'll let you work through that. I don't think I'm going to form groups. I'll just let you work on it where you are. I don't think it's going to take that long. And if you have questions, you can send it via chat, or you can speak out. What I will do is work through the problem, the bullet points, at a slower rate than you, so you can at least get hints if you get stuck. So I'll let you go to work. And again, if you have questions. One thing I should say is that when you look at the tangent line, look at it this way, using XY coordinates. And the point of tangency in XY coordinates is going to be R0. So just keep that in mind. It's not going to be R2 pi. Because obviously it's on the x-axis, which is why it's got a y coordinate 0. And let me know if you get an answer for the slope, or when you do. Oh, I gave you the wrong formula. Damn. There should be an R here. There should be an R right here. So here, let me write in a different sheet. And that's a little r there. So r of 2 theta. That's what I forgot. I apologize for that.
The sheet says the denominator is dr over minus
Yeah,
sine theta.
yeah,
Okay, because you have it written that you have plus theta on the denominator.
that's going to be 0. So I was just being sloppy because of that, but that's my fault. That's the typo right there. Thank you. So when I plug everything in, I got my tangent was equal to 2 pi, the slope of the tangent line. Again, what your goal is, the reason you're finding the equation of that line is so you can find this point, and you want to show that this is circumference and that that's the radius. And so that shaded triangle would be equal to 2 pi, would be pi r squared, area of the circle. That's where you want to end up. And again, Archimedes did this entirely geometrically. So a completely different way. I'm just showing that if we use modern methods, we get the same thing. And again, when you get to that point, let me know. And if you have questions about it at any point, let me know. So if you get stuck, you can send me a chat or ask me a question. Okay, it's about, there's one more thing I want to do today. So I think I want to bring this part to an end. So I'll go over things. But were you able to get to this point?
Yes.
Okay.
Yes.
Okay. And if you're not, that's fine. If everybody did, I'm not going to go through it. But I'm happy to go through it if people think it would be helpful. I'll do it quickly. Okay, good. So here's the idea. We want one turn here. We want this distance here to be r. So we want this to be the point r0. And so we figure out that since we want to end up at r when we go 2 pi, one turn of the spiral, we have to have this equation. Okay. Then we want to find the tangent at this, and using the correct formula over here, we're going to be using where the point of tangency is going to be r2 pi, because here we're using polars. When we get to the line, we're using x and y, so we're going to use the point r0. Okay. Okay. And again, if you put a 0 in here or a 2 pi, it's going to give you the same answer. But you need the 2 pi here. So I took the derivative. It's just a linear equation, and I got r2 pi. I used this correct formula again. The sign is 0, so that turned, and this I can ignore. The 2 pi's here cancel when I plug in 2 pi. R theta is r over 2 pi theta. R of 2 pi is r of 2 pi over times 2 pi. So that cancels. So I'm just left with the r. This cancels, so I'm left with this 0, so I'm left with the r on top and the r over 2 pi in the bottom. That simplifies simply to 2 pi. So now I know that my equation of my line is going to look like this. Y equal 2x plus b. So if I plug in this point here, I can find my b. So y is 0. 2 pi x plus b is equal to 0. So b is minus 2 pi r. That's the y-intercept. Okay. The minus doesn't matter with the circumference because the length of this side of the triangle is 2 pi r. The length of this side of the triangle is r. So the area, circumference, times r over 2. As we saw before, that's pi r squared. That's what we want. So here's what's going on. Remember, Archimedes proved that the area of the circle is equal to the area of a triangle. But he couldn't construct the triangle. So then he uses, by the magic of the spiral, he's able to construct that triangle. Then you can use Euclid 214, and then you can produce a square such that this area is the same as this area is the same as that area. So modulo the fact of using a mechanical curve to create the spiral, he can square the circle. And again, the Greeks referred to this as mechanical because the curve is mechanistic. It's based on some kind of device, and that's what you saw in that picture, that where you had one arm that was you had a rotating triangle where one arm kept extending at a uniform rate. Okay. Okay. So questions about that? Does that make sense? And again, he created this curve and realized how useful it was. I don't know, we don't know about his thought process, but I think it's, it's pretty creative to figure out, oh, I'll just make this curve that rotates outward at a uniform rate as I'm rotating, in a circle. And and that'll trisect the angle and square the circle. And then he has to go and prove it. And again, he's doing all this work. We're using, algebra is really using variables to manipulate algebraic quantities. That's what it is as its core. So we're doing geometry with letters, and he did it sort of the old-fashioned geometric way. Okay, so hopefully that makes sense. Again, in these situations, without seeing anybody, I have no idea whether what I did made sense or not. My hope is it did. My faith in you is that it did, but we'll see. If you have questions about it, please let me know, and I'll be happy to go over it. Okay, so what I want to do next is I want to trisect the angle. And here's to trisect an angle is you take a given angle, arbitrary, and what you do is you construct an angle that's equal to theta over 3. Okay, now you can bisect. It's a very simple thing to bisect. I can't remember the technique, so I'm not going to do it. But basically, I think you just draw a circle there, then you bisect the circle, and then these two angles are going to be equal. So that would be theta over 2 over here. And that's somewhere in book, and I'm pretty sure in book 1. Okay, so it's a simple construction. Trisecting, you know, it turned out later that trisecting was impossible by ruler and compass. Nonetheless, they persisted and tried to figure out there were a couple of different ways that people figured out to make mechanical curves to do this. Archimedes did it with a spiral. And I want to show that spiral on Desmos, so I'm going to share. But before I share, any questions about sort of what the basic problem? I mean, it's a relatively simple problem. Given an angle, trisect it. Okay. Actually, I'm going to go here. Okay, first I'll go to Blackboard. Are you seeing Blackboard now?
Yes.
Yeah.
Thank you. In the Archimedes trie section. Okay. So here's, oops, let me turn it all off. It's no fun. Okay. Okay. Good. Okay. I think you'll have more real estate if I do it that way. Okay, good. Okay, so what you do is first you make the basic spiral. And let's say that theta, I rotate the spiral as many degrees. I rotate it to form the angle that I want to trisect. And so I want to trisect this angle, you know, that's formed by the x-axis and the blue line. I want to trisect that. Now, it turns out that you can trisect the line. I can trisect the line segment between where the circle hits the line in the origin. I can use ruler and compass to trisect that. And so that's going to be the point of trisection. Then what I do is I use that as my radius and I draw a circle. Okay. And then what I do is if I look at where the circle intersects the actual spiral, I form that angle, you know, which is the black angle. That angle is going to be 1/3 the original angle. So that's a clever method. Again, I'll go through it real quickly. You rotate r theta until you get to the, sorry, let's go down here. Yeah, let's go down here. You rotate r theta to where theta is the angle you want to trisect. I use pi over thirds just as in the demonstration. Okay. And so that's where it hits the circle. And then I draw, sorry, let me start again. Okay. So I rotate the spiral theta, and then I create the intersection between a line segment from the origin and that point where I stopped. That angle is theta radians, or theta, whatever you want to think of. And then I trisect it, which again is legal move and ruler and compass. And then I draw the circle through the point of trisection. I see where the circle intersects the spiral, and I draw a line there. That angle is going to be the angle formed by the black is going to be 1/3 the angle that's formed by the original. Okay. Okay, does that make sense as a construction?
How do we arrive at this particular spiral again?
Okay. It's just the regular garden variety spiral, r equals theta. Because I want to let's say I want to bisect an angle of theta. Let's say I want to bisect the angle pi over 3, okay? But imagine it's going to be some unspecified angle. So I rotate the spiral r theta, and this point right here is going to have, it's going to be the point, since r is equal to theta, it's going to be theta theta right here. So the angle that line makes with the origin is theta radians. Does that answer your question?
I think, maybe.
Yeah. I mean, you could use, you want to use the simplest spiral possible. You just want to bisect an angle of theta. So you could use r is equal to 2 theta or 10 theta, but then you would have to compensate for that extra factor. And the radius is equal to the angle. That's what a spiral is, or a multiple of the angle. Okay, and I'll go through this on pencil and paper. And then do the trisection and everything else. Okay, so are there other questions? Okay, and your goal is going to be to show that this works. It's a lot less involved. But the fact that the radius is equal to the angle can be confusing. Okay, so I'm going to stop the share. And I'm going to start with my spiral r equals theta. I want to trisect an arbitrary angle theta prime. So what I do, remember I just plug theta prime and I take the spiral only as far as theta prime. So again, let's say this is my theta, this point here. This is my angle theta prime, or theta 0. The point here, the angle is theta prime, and the radius is also theta prime. I keep saying theta prime, theta naught is what I mean. Okay, I'm going to try to get a better focus on my camera. Okay, and so then I trisect. I draw this line segment here, and I trisect, and I'm just going to assume it's right about here. So I'm going to draw it here. There's that, and let's say that's the point of trisection right here. So this would be, again, radius and angle are the same. So theta naught. This angle is theta naught. Okay, so then I've trisected this right here. So remember, this length here is the radius. The length of this segment, let's call this point P and 0. The length of P0 is equal to the radius, which is equal to the angle, because that's what that function does. Okay, so what's the length here going to be? If I trisected the segment of theta naught, what's the length of the trisection? Well, it's just going to be 1/3. It's going to be r over 3. If this is r, and that's just theta naught over 3. And then I draw the circle here, through here. The circle's radius is fixed at theta prime. So I look at to see where the circle intersects the spiral. I claim that this angle here is going to be theta naught divided by 3. And I want you to sort of convince yourself using math that that's the case. The intersection of the circle of radius theta naught over 3 with the curve r equals theta produces this angle, theta naught over 3. And the calculation isn't complicated at all. It's more thinking about it. It may be complicated, it may not be. So I want the intersection of r equals theta with the circle r equals theta naught over 3. In polar coordinates, the equation for a circle is just its radius. If you have a circle of radius 1, its equation in polar coordinates is r equals 1. So it's very simple in polar coordinates. In polar coordinates, if I just take any point up here, it's r theta. This length is r, this angle is theta. That's why this angle here is theta naught. Because my coordinate is theta naught, that means both the radius and angle are theta naught. So what's the intersection of these two curves? If you set them equal to one another, what does theta equal? And again, you just set the r's equal.
It'll just be theta naught over 3.
Yeah, yeah. And again, if you're not used to polar coordinates, haven't used them very much or at all, this is strange. And maybe I should have gone into more of what polar coordinates are. But a polar coordinate, if you take a point in space, it's the radius, the distance from the origin, and the angle. So with this spiral, any point on that spiral is both, it's going to be like the line y equal x, they're going to be the same. And the radius is the same as the angle. Again, okay, so again, the point here is that he was able to use the spiral, create this curve to solve, you know, there's the fact that you're not using ruler and compass, so it's not a true solution, but he was able to sort of show how to do it if we expanded our mathematical vocabulary to include this curve, then angles trisected, circles are squared. Okay. Are there any questions on that? I just wanted to talk a little bit about Archimedes. I won't talk very much. I have some material to post on that, and I'll let you read that. But I do want to say a few things about him. Okay. But questions about these? Okay. And I thought it would be interesting, since we talked about curve doubling, and the three big unsolved problems were doubling the cube, squaring the circle, trisecting the angle. Those were the three biggies. And we saw that the cube doubling is solved by conic sections, parabolas. So using conic sections, we could then double the cube. And then trisecting and squaring the circle are solved by spirals. And Euclid, Archimedes wrote a whole book on spirals, a lot of which I think still is around. Okay. So just a few things, and again, I'm not going to talk all day like I did when I was talking about how Greek math transitioned from 500 to about 300. But he found formulas for circles, spheres, cylinders, and cones. And he discovered or invented, depending on your philosophical point of view, pi. So he was the one, as far as we know, that realized that what pi was in the way that we would think of it. He saw pi as the ratio of the circumference over the radius, which, I'm sorry, over the diameter, which is immediate if you do that. That's how he saw it. And he was able to show, I think this is what he showed. I should have looked it up. Something like this. I don't think it was 219 over 70, but it was close. And it's an amazing, difficult computation. He used a 96 gon for his computation. Okay. And then you've probably done these things in calculus where you do a rotation around the x-axis. He didn't do it that way. He did it a different way. Again, it would take a couple of classes to really do it justice, so I'm not going to do it justice. I'll just give you his formulations, but not his reasonings. Okay. He showed, see if I can remember this, the precise formula. So this is a parabola. And he showed that 4/3, these are just two random points, that 4/3 the area of this triangle is equal to the area under the curve. And what he did is he set up a lever. Give me a lever big enough I can rule the world. He articulated a lot of the laws of the lever. It was a balancing thing. And I can't remember precisely the distances, but he thought of area as weight. And so he found a balance point between this and this. So if this was length L, this was length 3/4 L. So that was the balancing point. And he would move a tiny bit of area from here over to here. That's the rectangle. And then move this longer area over here. And he did this, of course, I'm talking about like he actually did it physically. He did it computationally, mathematically. He also found a series to measure the area between the parabola and the triangle. Remember, you know the area of the triangle, that's easy. So he figured out what these areas were using an infinite series. Okay. So again, and he did this traditionally ruler and compass. He did it with the series, and he did this. And the way that he did this is called his method. And that was lost for a really, really long time. All we saw were his results. There's a notebook where he figured this out, where he did that balancing act I'm talking about. And that was, you'll find out more about that. Okay. So he found tangent to the spiral. Remember, we used a tangent line? He knew properties of tangents, as did Apollonius. So the point I'm trying to make here is that if you think about some of the things that we think of as making calculus, using infinitesimal arguments, finding tangents, finding areas, he did all that. He was able to do all that for things like spirals and for things like parabolas. He didn't have a universal system the way that we do for finding areas once we know the equation, but he was able to do it. So he lived around, again, I think it's worth pointing out, he died in about 212 BC, and he was killed by Roman soldiers. He lived in Sicily, and he spent a lot of time, he was like in his 70s, I think, and he developed a lot of war technology to defend the Greeks living in Sicily against the Romans. Sicily was a Greek empire, was part of the Greek empire at that point. The Romans wanted it because Sicily is at the bottom of Italy. And so they came and attacked, and he built all these devices, these weapons, really. Like some people say he built a fire array that, using magnifying glass in the sun. He built pulleys that would go down and grapple a boat and pull them out of the water. But eventually the Romans won, and they were supposed to save Archimedes. They were given orders, but some soldier killed him, not knowing who he was, according to the story. And that soldier did not meet a happy fate, because the Romans wanted his expertise, much like we used Nazi scientists after World War II to help our weapons technology. They wanted Archimedes to help their war technology. They didn't care about the math. Again, I'm not comparing him to a Nazi by any means. But what happened with the mystery is that these ideas seemed to die out when he was killed. And I don't know whether they were too complex for other people or what happened. And I'll talk about that at some point. But these ideas just died out. And so I always like to play what ifs. And one of my what ifs is, what if these ideas hadn't died out? What if the Romans saved him and were more interested in his math than in his war technology? Would we have had calculus 2,000 years earlier, or 1,500 years earlier? But that's not the way it happened. Okay, so that's all I have to say today. I will post some material about Archimedes. I did locate the film, and so I'm gonna have you look at the film and answer some questions about it. We'll discuss it at some point. And I'll have all that information out, and you'll have class time to watch the film. So I'll just have you watch it on your own, and that'll count as probably a whole class, because it's a little bit over an hour. And then I have some questions to answer, and then there's a project which I will have you do on that, and that will probably be done. That might be the last thing you do in the semester. It might be part of the final project, and I'll probably have that be individual, but maybe let people work on it in teams if they want. But again, I'll write all that up. I just wanted to give you a sense of where we're headed. So on Thursday, I hope to just wrap up the Greeks briefly, and then start Arabic mathematics, and then we'll probably do the Archimedes thing after that. But I may flip it, but I will let you know. So questions or comments, anything like that before I go? I'm gonna urge you. I have a perfect record so far this semester about submissions. Nobody not submitting any important thing. So if you haven't done your homework and haven't submitted it, please get in touch with me. Even if you're stuck on some stuff, I'll be happy. I want you to submit it. And so if you haven't submitted it, just get in touch with me and we'll figure out, we'll get you over whatever the hump that you are in. Okay, that's all I have. So have a good couple of days, and I'll see you on Thursday.
Have a good day.